The smartest LLM strategy is not always choosing the biggest model. For narrow, repeatable workflows, a smaller open-weight model can be cheaper, faster, and just as accurate. If you choose it carefully, fine-tune it well, and validate it before production. So far, we've moved from diagnosing fragile LLM apps to designing controlled inference. Those failures were not random. Exploding token costs, latency spikes, timeouts, GPU memory errors, drift, and regressions all point back to weak architecture. Now we turn to model choice, because the model you pick shapes cost, serving complexity, hardware needs, latency, and quality. Choosing a model means choosing part of your system architecture. A larger model may improve quality, but it also changes GPU memory needs, batching strategy, latency, and cost per request. A weaker model may seem cheaper until you need longer prompts, more tool calls, retries, or human review to make it reliable. Licensing and deployment rules matter too, especially when customers require data residency, private hosting, or auditability. The best model is the one that fits the task, the risk level, and the operating constraints of the product. Instead of starting with a leaderboard, start with the work. Name the task: extraction, classification, summarization, coding, retrieval, or reasoning. Then define the operating limits. How fast must the model respond? How long are the inputs and outputs? How accurate must it be? And what happens when it fails? Separate the everyday workload from the rare, messy edge case. A model that handles common tasks cheaply may be better than a larger model used everywhere. Benchmarks are useful signals, but your domain data should decide. Once the task is clear, evaluate production fit across several dimensions. First, quality. Does the model answer domain questions accurately, handle messy inputs, follow formats, and refuse appropriately? Then cost and hardware. Memory footprint, throughput, batching, quantization, and whether your target accelerators can actually serve it. Also test context behavior, because long context windows often degrade before they reach their advertised limit. Finally, verify the license and ecosystem. Commercial rights, redistribution rules, documentation, community support, and serving compatibility can determine whether a promising model is deployable or a future operational risk. A practical selection process starts broad, then narrows quickly. Include a few size tiers, small models for speed and cost, mid-sized generalists for balanced performance, and larger candidates as quality fallbacks. Apply hard filters before spending time on deeper evaluation. Remove anything with incompatible licenses, unsupported runtimes, insufficient context length, or hardware requirements that do not fit your deployment target. From there, prioritize reliable tokenization, stable instruction following, and active community or vendor support. Keep one commercial API baseline, so offline candidates can be compared against a known quality and cost reference. Model size should follow the work, not personal preference. If a workflow is repetitive, high volume, and has predictable inputs and outputs, a smaller tuned model is often faster, cheaper, and easier to control. Think classification, normalization, structured extraction, or templated summaries. When the task involves ambiguity, multi-step reasoning, synthesis across sources, or unusual edge cases, larger models may earn their cost. The practical move is routing. Send simple work to efficient models, escalate harder cases to stronger models, and revisit that boundary as the workflow matures. Fine-tuning helps when the same product workflow happens again and again. Instead of packing every prompt with policies, examples, formatting rules, and edge cases, you train the model on real input-output examples from that workflow. Over time, those repeated instructions become part of the model's default behavior. This does not make the model smarter in every sense. It makes the model more consistent for this specific job. Prompts get shorter, outputs become easier to validate, and teams spend less time on retries, corrections, and downstream cleanup. Fine-tuning works best when the examples match the job you want the model to do. A smaller, cleaner dataset often beats a huge, noisy one. Keep successful production conversations, expert-approved answers, support workflows, edge cases, refusals, and structured output examples. Remove anything that teaches the wrong lesson. Contradictory labels, outdated policies, personal data, or cheap synthetic filler. Then split the data. Train on one portion, tune decisions on validation, and reserve a locked evaluation set so you can measure real improvement instead of memorization. Treat fine-tuning like a controlled release process, not a quick model upgrade. First, measure the base model on a locked evaluation set, so improvement is real, not anecdotal. Then curate examples for stable, recurring behavior and run supervised fine-tuning, which is usually the safest first step for product workflows. After training, validate against the same evals, then run regression tests to catch new failures. Every run needs versioned metadata, model, data, parameters, scores, and deployment notes. That trail is what turns experiments into a production candidate. One major cost win from fine-tuning is that you stop paying for the same instructions over and over. Long prompts often carry examples, formatting rules, domain context, and safety guidance on every request. After tuning, the model can internalize much of that stable behavior, so each call only needs the specific task and user input. That can cut prompt tokens dramatically. For example, from 2,400 to 650, which lowers latency, reduces serving cost, and increases throughput. Validate carefully, though. Shorter prompts must still preserve safety, formatting accuracy, and edge case behavior. Before moving live traffic to a smaller or self-hosted model, prove it offline. Build a golden dataset from real production requests, hard edge cases, and customer journeys where mistakes matter. Generate candidate outputs, then score them with deterministic checks, judge models, and human review for nuance. Compare against your current production model, not a generic benchmark. Finally, set explicit migration gates: minimum quality, maximum critical failure rate, acceptable latency, and real cost savings. If the candidate fails any gate, keep traffic where it is. Evaluation works best as a layered control system, not a single score. Golden datasets provide repeatable benchmarks, so every model or prompt change faces the same test. Rubrics turn fuzzy quality into observable dimensions: correctness, completeness, tone, format, and safety. Judges help scale review across many examples, but they must be calibrated against human labels, because judges can inherit bias or reward the wrong behavior. Human review is slower and more expensive, but it is essential when risk is high, intent is ambiguous, or approval has consequences. Reliable replacement comes from combining these methods, then watching drift over time. Self-hosting is a tool, not a default. Use it when traffic is predictable, volume is high, latency matters, or data sensitivity justifies tighter control. Avoid it when the workload is small, irregular, or depends on frontier reasoning that changes quickly. The hidden cost is operations: GPU capacity, patching, upgrades, monitoring, incidents, and people on call. A strong production pattern is hybrid. Keep stable, high-volume paths on your own infrastructure and send rare, complex, or fast-evolving cases to an external API. Model selection and fine-tuning are the bridge from cost awareness to reliable self-hosted inference. Choose models by task fit, license, cost, hardware, context, and ecosystem. Fine-tune when repeatable workflows can use shorter prompts and smaller models. Before shifting traffic, gate changes with offline evaluation. Next, we'll serve efficiently with VLLM, then optimize through quantization, batching, routing, fallback, auto-scaling, and capacity planning.